Lying dormant in the northern region of the stone quarries of Aswan, Egypt, is a single piece of carved pink granite. It is known as the Unfinished Obelisk. According to the Egyptian Supreme Council of Antiquities, the monument measures 42 meters in length. Had it been fully detached from the bedrock and erected, it would have weighed approximately 1,200 tons. This is the equivalent weight of 3 fully loaded Boeing 747 aircraft, carved into a single continuous spire. The standard archaeological explanation dictates that this monument was commissioned by Queen Hatshepsut in the 15th century BC. The accepted method of excavation proposes that hundreds of workers used round, handheld balls of dolerite, a rock slightly harder than granite, to continuously pound the bedrock. They purportedly bashed away the stone inch by inch to create the deep trenches surrounding the obelisk, intending to undercut it, pry it free using wooden levers, and drag it to the Nile. But the physical reality of the site immediately fractures this logistical model. The trench surrounding the obelisk is narrow, measuring barely 70 centimeters wide in some sections. To pound granite with a dolerite ball requires swinging the stone with sufficient force to crush the crystalline structure of the bedrock. In a trench less than a meter wide, a worker physically cannot swing a heavy stone ball with enough momentum to fracture granite. There is simply no room for the biomechanical leverage required. Furthermore, the bottom of the trench curves inward beneath the obelisk. How workers were supposed to swing heavy stones upward, fighting gravity in a cramped, dark crevice underneath a 1,000-ton monolith, remains a severe mechanical paradox. The project was ultimately abandoned when deep cracks appeared in the granite. No modern engineering team has successfully attempted to excavate a 1,000-ton obelisk from solid bedrock using only handheld pounding stones in a 70-centimeter trench. Carved into a solid granite hill in the Bihar state of India is a subterranean chamber known as the Lomas Rishi Cave. According to the Archaeological Survey of India, it was commissioned during the Mauryan Empire in the 3rd century BC. The physical anomaly of this site is not its age, but the interior surface of the stone. The walls and arched ceiling of the inner chamber are polished to a literal mirror finish. This is not a general smoothness. It is a highly reflective glass-like surface cut into one of the hardest natural rocks on the planet. The standard archaeological explanation requires us to believe that this polish was achieved using iron chisels, fire setting to weaken the rock, and years of continuous, grueling manual abrasion using sand and water. We know the Mauryan Empire possessed advanced stoneworking guilds. We know continuous friction can eventually smooth granite. But the physical evidence inside the cave tests the absolute limit of that theory. The granite is not flat. It forms a complex, sweeping internal vault. To maintain a perfectly uniform distortion-free mirror polish across a dark, curved subterranean surface requires immense, sustained, and evenly distributed pressure. Modern fabricators achieve this using diamond grit polishing pads spinning at thousands of revolutions per minute. Here is the counterintuitive reversal. The technology to perfectly polish curved granite vanished from the Indian subcontinent shortly after these caves were carved. Later structures, despite belonging to more technologically advanced empires, never reproduced this exact glass-like uniformity. High in the Andes of Peru lies the megalithic fortress of Sacsayhuaman. Constructed by the Inca Empire in the 15th century, the site features zigzagging terrace walls built from massive andesite and limestone blocks. The largest of these stones are estimated by the Peruvian Ministry of Culture to weigh between 100 and 120 tons. But it is not merely the weight that defies expectation, it is the geometry. The walls are built using polygonal masonry. The stones are not cut into uniform rectangles. They are irregular, multi-sided shapes, some featuring up to 12 separate angles. They lock together without a single drop of mortar. The joints are so meticulously crafted that they have survived centuries of devastating Andean earthquakes, the stones shifting and then settling exactly back into place. The official archaeological explanation is that the Inca shaped these stones using river cobbles to pound the edges, hoisting them onto earthen ramps to test the fit, and then lowering them back down to scribe and grind the connecting surfaces until they matched perfectly. Here is the counterintuitive reversal. To perfectly scribe a complex, irregular joint, the stones must be brought together. To adjust the fit, a 100-ton stone must be lifted away, pounded with a smaller stone by hand, and then precisely lowered back into place. To achieve the paper-thin, zero-clearance joints seen at Sacsayhuaman, this process of lifting, checking, and lowering a 100-ton irregular polygon would have to be repeated hundreds of times for a single block. We know the Inca did not possess iron tools, the wheel, or written mathematics. We know they used earthen ramps and human labor. But modern stonemasons, using diamond-tipped saws and hydraulic lifts, struggle to reproduce multi-ton polygonal joints with this level of seismic perfection. If the standard tools could not practically execute this repetitive testing process on blocks the weight of a diesel locomotive, what could? At an altitude of nearly 4,000 meters in Bolivia, the ruins of Puma Punku sit shattered across a high plateau. Built by the Tiwanaku Empire, the site features prefabricated blocks of red sandstone and andesite. The University of Pennsylvania Museum of Archaeology and Anthropology confirms that the largest of these stone slabs weigh up to 131 tons. The anomaly here is not merely the weight, it is the material and the cuts made into it. Andesite is a highly abrasive, dense volcanic rock. On the Mohs scale of hardness, it is incredibly difficult to work without specialized equipment. Yet scattered across Puma Punku are the famous H-blocks highly geometric stones featuring perfect right angles, sharp internal corners, and precision-drilled blind holes of uniform depth. The mainstream explanation holds that the Tiwanaku shaped these stones using harder pounding stones, sand acting as an abrasive, and plumb bobs for alignment. They rubbed the surfaces flat over months or years of continuous grinding labor. But here is the physical problem with sand and pounding stones. You cannot pound a perfectly sharp internal right angle into a hard volcanic rock. Pounding tools are round. Abrasion leaves concave, sloping corners. To achieve a crisp, 90-degree internal cut in andesite where three planes intersect precisely at an inside corner requires a tool that physically fits into that corner. Modern fabricators achieve this using diamond-tipped router bits and high-speed rotary tools. At Puma Punku, these sharp internal corners exist. A ruler placed along the recessed channels sits perfectly flush against the stone. The drill holes are evenly spaced and completely smooth. No independent replication attempt using copper chisels and pounding stones has produced the sharp internal geometry seen on the H-blocks. If this knowledge of precision stone cutting existed here, isolated high in the Andes, how many other places possessed it? And why did the technique vanish completely from the archaeological record? Thousands of miles away from the Andes, in the Bekaa Valley of Lebanon, lie the ruins of Baalbek. In the foundation of the Roman Temple of Jupiter sit three massive limestone blocks known as the Trilithon. Measurements confirmed by the German Archaeological Institute put the weight of each block at approximately 800 tons. That is the equivalent weight of two fully loaded Boeing 747 commercial aircraft per stone. What separates the Trilithon from abandoned monoliths is that these stones were successfully moved. They were transported from the quarry, raised 7 meters into the air, and set into a retaining wall with joints so tight a razor blade cannot be slipped between them. Mainstream archaeology provides a specific, documented explanation for Roman lifting technology. The Roman architect Vitruvius described complex cranes powered by treadwheels, where multiple men would walk inside a large wooden wheel to generate lifting force. The Orthodox defense argues that the blocks at Baalbek were moved using exactly these methods, merely scaled up. But this is where the physical evidence tests the absolute limit of the theory. A wooden treadwheel crane has a maximum structural load. Beyond a certain weight, the timber snaps, the wooden gears shatter, and the thickest hemp ropes shear. Modern crane companies using tracked hydraulic crawlers, forged steel cables, and computerized load balancing systems require months of site preparation to lift an 800-ton object safely. The counterintuitive reversal is the complete lack of documentation for cranes of this magnitude. The Romans were meticulous record keepers of their engineering triumphs. Yet there is no text, no blueprint, and no structural remnant of a crane capable of lifting 800 tons anywhere in the Roman archive. No experiment using the wooden tools available in the 1st century has successfully produced a lift of an 800-ton block to a height of 7 meters. If the Romans actually possessed mechanical cranes capable of lifting 800 tons without catastrophic failure, why was this capability never documented in their meticulous engineering records, and why was it never used again anywhere else in the empire? We now know that the physical record contains objects of a mass, geometry, and logistical complexity that push the assumed capabilities of their respective eras to the absolute breaking point. We do not yet have verified mechanical models using period-accurate tools that can physically reproduce the extraction of the Aswan obelisk, the sharp internal corners of Puma Punku, or the 7-meter elevation of the Baalbek trilithon. These sites connect to a larger, cross-cultural pattern, advanced logistical and architectural techniques that appear in isolated pockets of history, achieve impossible heights of engineering, and then completely vanish, leaving later, supposedly more advanced civilizations unable to replicate them. What this tells us is not that ancient civilizations were more advanced than we give them credit for. It is that the distance between what they built and what we assume they could build is measurable, and the gap is real. The gap is in the physical record. It is not going away. If this video gave you a specific fact you will repeat, a gap you did not know existed, a question the evidence raised that no explanation has yet closed, share it with someone who would want to follow the trail. Understanding the actual capabilities of ancient civilizations requires us to measure the physical stone, rather than simply accepting the established narrative. Leave a comment. Which of these 5 ancient ruins do you think provides the strongest physical evidence that a highly advanced understanding of structural engineering existed before the timeline currently accepted by mainstream archaeology? In a future investigation, we will examine a sunken landmass in the North Sea, where dredgers have pulled up human tools from a landscape that has been underwater for 8,000 years. See you at next one.